Welcome back to numerical analysis, everyone. Today I wanted to focus on the practice problem that I left you with at the end of the last lecture. You may remember we had been talking about how you could take a differential equation, and rather than jumping in and trying to solve it right away, you could just find out some information about all the derivatives of a function from the differential equation itself. And I had left you with this practice problem where we have an initial value problem given this way: dx dt is x plus t squared, and when t is equal to 0, x is supposed to be equal to 1. So this is an initial value problem. And I wanted you to see if you could find the values of the nth derivative of x evaluated at 0 for every non-negative integer n. So n equals 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So obviously, you have to look for a pattern here. If you follow through with this, you'll see that one develops. So we did a little bit of this in the last video, just to kind of emphasize the idea that there's more information in the initial value problem that might meet the eye. First of all, it gives you that x of 0 itself is 1. So you think of x, the function x as its own 0th derivative. So we certainly have the 0th derivative. And it may not be surprising to see that you can get the first derivative as well, because you have something about dx dt. So if you wanted to evaluate x prime at 0, well, that's dx dt evaluated at t equals 0, and then use the ODE. Dx dt is x of 0. This is not a multiply here. It's x of 0 plus t, which is 0 squared. And that turns out, and then x of 0 is 1 from the initial value. And so x prime of 0 is 1. In the next step, to find second derivative information, you have to first take a look at the second derivative, but you can get that from the ODE as well. So the second derivative is the derivative of the first derivative, but we know from the ODE that dx dt is x plus t squared, and so we're getting, that's where that's coming from. And then bring the derivative inside. The derivative of x with respect to t is dx dt, and then plus 2t. And again, use the same ODE here to say dx dt is x plus t squared. And so now you have an expression for the second derivative. Plug in t equals 0, so it would be x evaluated at t equals 0, which again is 1, 0 squared plus 2 times 0. So again, you're getting 1. And I basically left you at the third derivative to take it from there. So let's just kind of pick up on that real quick. Look, first compute the third derivative. So it's the derivative of the second derivative. We just found that the second derivative was x plus t squared plus 2t. And so the derivative of that would be dx dt plus 2t plus 2. And so again, dx dt here is from the original ODE x plus t squared, right? So that's where that comes from, and then you still have the 2t plus 2. So the third derivative is x plus t squared plus 2t plus 2, and so the third derivative evaluated at 0 would then be x of 0 plus 0 squared plus 2 times 0 plus 2. X of 0 is still 1 from the initial value, the initial condition. So now we're getting 1 plus 0 plus 0 plus 2, or 3. So the third derivative evaluated at 0 is equal to 3. Now, something interesting happens from this point on out, and let me see if I can show you. Again, you just start in the same way. So the fourth derivative is the derivative of the third derivative. There's the third derivative from the step we just completed. Now, if you take the derivative of that, of course, you're getting dx dt plus 2t plus 2, and dx dt is still x plus t squared, so you're getting x plus t squared plus 2t plus 2. Does that look familiar? I guess I'm going all the way down here now. this was the same result we got for the third derivative. For this particular function, its fourth derivative is the same as the third derivative. And so we're not surprised that the fourth derivative evaluated at 0 turns out to be the same as the third derivative evaluated at 0. Well, once that happens, once the fourth derivative is equal to the third derivative, then the derivatives from there on out are also going to be equal to the third derivative. Why was that? Well, think about the fifth derivative. That would be the derivative of the fourth derivative, but we know the fourth derivative is equal to the third derivative. So the derivative of the third derivative is again the fourth derivative, but we know the fourth derivative is equal to the third derivative, and so the fifth derivative is equal to the third derivative. Would you like me to repeat that? The fifth derivative, I'm not really going to repeat it. You can see though how once the next derivative becomes equal to the previous one, the chain will continue in this case. So in the same way, all the derivatives past 4 are going to be equal to the third derivative. And so when you evaluate them at 3, when you evaluate these derivatives at 0, they're all going to be the same as the third derivative at 0, which was 3. So we can summarize all this in one nice little conditional equation. What we found out is that the nth derivative of x evaluated at 0 is 1 if n is either 0, 1, or 2, and it's 3 if n is greater than or equal to 3. And so, yeah, we have information about all the derivatives of this function, all coming from that initial, the original initial value problem. In principle, every initial value problem works like this. You can get information about all the derivatives just straight from the initial value problem itself, along with a little work, in taking derivatives. So the question now will be, what do we do with that information? How can we use it to find out something about the solution? And that will be the subject of our next video, which will be coming out to a theater near you very soon. So stay tuned, stay healthy. If you have questions, let me know. And best wishes. I'll talk to you again very soon.